Hello everyone. This is a live stream for BUSN 6630 Operations Management. I'm Dr. Harper, and today we're covering business forecasting. Now this is a live stream and this will be recorded, and I do have a chat room for anyone who wants to ask questions. We can go live. I'll go through the chat room and answer questions if I can. But I also have office hours Monday, Wednesday, and Friday evening at 7 p.m. with a link to Zoom office hours where we can have a conversation about it. And so this lecture is a live stream, as I mentioned, on YouTube, but also we can have a conversation on Zoom. So I'm using both. Okay, so let's get started. First of all, let me bring up Canvas. And in Canvas here, we have, if you come down to this week, weeks 2 and 3, forecasting, and notice what I've done here under videos. We have the business forecasting. Here's the lecture that I'll be doing tonight. So this is a Word file. And then this lecture, this stream, will be rendered as a video, and the link will be right here. So notice it's black. Black is not live. The blue is live. So all these are live. Well, this is a live to download a Word file. This one I don't have a live here. This will be live for a video. You view it, it goes right to YouTube, and you can see the video. And so this will be recorded. Now notice I've already put in the forecasting for quiz 1, homework 1, and assignment memo 1. And so all three of these will be part of forecasting. But also notice that quiz 1 is due February 7th, which is this Sunday. But homework is not due till February 14th. And assignment 1 is the response memos are not due till February 21st. I went ahead and put all these here, and I'll probably keep repeating them and keep copying them and putting them later. So once quiz 1 is submitted, I won't put it up anymore. But I'll continue to put up homework 1 and memo 1. Okay, and the reason is, let's bring up the syllabus. Okay, bringing up the syllabus here, coming down. Notice that here we are on January 26th, but quiz 1 is due next Sunday. Okay, but then homework 1 is due the Sunday after that. The memo is done the Sunday after that. So I spread things out. And the purpose of that is so you can learn it as much as you can, and also for me to give you help as much as I can. And so I spread things out, but I do overlap things. So remember, quiz 1 is going to be mechanics. You can look at it. Homework 1 is going to be the application, and that's progressive. It starts with just definitions, and it works problems in a progressive manner. You can see that. And then memo 1 is going to be more communication, creating a memo and everything. And I'll talk about that. Now, next week, the week of February 2nd on the live stream on Tuesday, that's when I'll be talking about the quiz 1. So that'll be a short one. I'll just be talking about the quiz. It'll take 30 minutes. It won't be very long. But the week after that, I'll do linear programming and optimization, and I'll do homework 1. For forecasting. Notice homework 1 is forecasting. But I'll do linear programming, and then I'll do homework 1. So I'll do both of those. And then the second week, I'll do linear programming for quiz 2. I'll also do memo 1 for forecasting. So again, I keep overlapping these things. And so each second week, I will do the assignments. So the first week of the 2-week type of a design, the first week is going to be the lecture, and then the second week is just going to be focusing on the assignments that are due that week. For example, the week of February 2nd, on February 2nd, that live stream is quiz 1. February 16th is quiz 2 and memo 1. Well, I'll also do homework 1 here. So that's how I've done it. It seems to have worked well in the past, and I think it'll work well this time. You have plenty of time to work each of these and move on to the next. Okay, So here we are. Let's come back to forecasting. So today, what I'll be doing is just going through forecasting. In forecasting, we'll be using Excel, as I mentioned. And I'll bring in Excel every once in a while to show how to do it, but I won't go into it in depth. When I talk about the quiz, we'll do the mechanics. Homework, I'll go deeper into the mechanics. And then the memo, deeper yet into the mechanics, and also presentation and on graphs and things. And so you'll see as we go through the course. Good. Okay, here we go. So let's download the forecasting, and let's bring up this Word file. This is a lecture for tonight. Okay, I've already downloaded it. Let me bring it up over here. There it is. Okay, here we go. First of all, this first page is like an overview of what I'm covering. Not everything I'm covering, but a highlight of what I'm covering. I start with 6 terms here. And these 6 terms is an introduction. And then I have this table. Well, the first 3 rows of the table are a time series, and I define stationarity, components, and techniques. And then I go through each one of these. But I illustrate the 3 time series to illustrate each of these. I call them my introductory examples. So this is just a really introduction to those terms, the terminology, an introduction to the time series, the terms and how they're used, and also down here the problem-solving approach. And then I'll do a first pass. The second pass I do through this table, I come over here and go in depth in each one of these techniques. And so that's going to be what I'm covering tonight. And I'll mention blocking and filtering, a little bit on REMA modeling. That's more advanced methods. But I will, well, this is what we'll be doing in this course. This is more advanced methods, extensions. We don't do them in this course, but I'll allude to them and show where they go. Okay. But the introductory example, I'll refer to this 5-step problem-solving process with forecasting. And I want to emphasize the 5-step problem-solving process because the way you solve problems is very different than understanding the material. And so identifying the problem, etc., like I did in the first few lectures. Okay, so this is like an overview of how I'm going to approach this course, the lecture today. Now, when I go through the techniques in more detail, well, today will be a first pass, or will be more detail. Next week, I'll probably go back to these when I talk about the homework or the quiz and the homework. That's when I go even more depth. So we'll just it's progressional. We keep going deeper, deeper, and deeper. Okay, so let's get going. Introductory example number 1, moving average. Okay, now these introductory examples, I made them very simple as I could, just to understand a framework. Okay, the second pass is where I go inside and start developing terminology and concepts. Okay, so first pass. Introductory example number 1, moving average. Here's my 5-step process. Okay, the way you apply this, first plot the time series. Well, we have a weekly time series. Now, I'm getting ahead of myself. I never talked about these terms up here. Sorry. The time series forecasting down here is just a series of data over time, and those data represent a business variable. Now, forecasting means predicting the future. Well, business forecasting really means predicting business future of some kind. And so the time series forecasting is looking at the data, a variable, over time, and saying, I'm going to look at the patterns in that time series and use those patterns to forecast the future. Causal forecasting, on the other hand, is looking at the time series, but then it's looking at other variables that influence that time series and that probably cause different patterns in the time series, and using those variables to forecast your time series. Now, there are qualitative techniques. We will not cover those in this course. However, some people every semester will look at some of the resources I have for the project, and they'll have qualitative approaches, which is great, going beyond the course for the project. The quantitative forecasting techniques, I will initially do the moving average, exponential smoothing, regression, and seasonal indexes. Now, the term intrinsic and extrinsic forecasting, I put in here to be complete, but intrinsic forecasting essentially is the same as time series forecasting. You're using the information in the time series, intrinsic in that time series, to forecast the time series. If there's a pattern, we use that pattern to forecast the future. If there's a trend, we use that trend to forecast the future. Extrinsic is the same as causal, just different words. Extrinsic using information outside of the time series to forecast the time series. Okay, now the reason I have intrinsic and extrinsic is some industries, some companies exclusively use intrinsic forecasting and get extrinsic. Well, you know what they mean now. Usually people use just time series and causal. You know what they mean. There's all different terms floating around. Okay, so now let's get into the introductory example number 1 here. Moving average. We have a weekly time series. Now, weekly time series, we have a time series over time, but a weekly says, well, this is week 1. So we aggregate the data over, it could be demand, it could be sales, it could be expenditures, but whatever you have, you aggregate that over 1 week and you report one number. I want to emphasize that this number is not just a number, it's a representation of something behind that number, something real. Like 24 homes that were sold by a real estate agency, or 24 people who were serviced that week, or 240 automobiles that were sold that week, or $24,000 in profit that we made that week, or 240,000 calls coming into a switchboard. But those numbers mean, they have a meaning. And so you can look at the numbers, but always remember those numbers represent a reality behind them. Okay, the first thing we do is plot the time series to determine stationarity. I plot it, and there it is. Up, down, up, down, up, down. So the idea here of stationarity says, well, the overall nature of this time series is flat. There's some variability. It goes up and down, but it starts at 24, it ends at 24, and so it's pretty much variable, but the overall nature of that time series is level, is flat. And that's referred to as a stationary time series. So we have a stationary time series. Okay, then the second thing is choose your components. Now, the definition of a component is a cause of variability. Well, we can see there's variability here. 24 from 1 to 2, it goes from 24 to 26. So the variability there is 2. 26 to 28, the variability is 2. 28 down to 24, the variability is a -4. So we have variability. What's causing that variability? What's the cause of it? Can we identify the cause? Well, if there is no real identifiable cause, if there's no way to explain it, if it's unexplained, then that variability is referred to as a random component. So a random component is unexplained variability, or an unexplained cause of the variability. Okay, the next is select the technique. Well, there's where the table comes in. If you have a stationary time series with a random component, then the technique is moving average or exponential smoothing. Initially, we'll look at moving average. Well, at this point, I want to emphasize here is where a lot of people in universities make mistakes, in school make mistakes, and a lot of people in industry make a mistake. The mistake they make, the practical mistake they make, says, oh, there's a time series. What technique do we use? So they jump to the third step. They jump to here first. Now, you can use the wrong technique on a time series, and that technique will give you an answer. But if it's the wrong technique on a time series, that answer would be incorrect or have enormous bias or would be misleading. So make sure that you understand the process to make sure you have everything set before you go to the technique. You know it's stationary. You know you have just a random component, no other components. Now I know I'm going to use moving average, and that's why I'm using moving average. You don't try something and see if it works. You say, I'm going to try this because I have an educated decision, like it's a stationary time series, it's a random component, I'm going to use moving average. Okay. Now the next step, once you've had your technique, you select your technique, estimate the parameters. Well, the parameters for a moving average is called the window. But initially, actually in this course, we're not going to calculate windows. We're not going to estimate windows. I say estimate the parameters because in some cases we will estimate parameters. We will today in this lecture. But in some cases we do not estimate parameters. In this case, we don't. The parameter is a window. Well, what's a window? Well, if we want to take an average of these numbers, and that average is going to be the forecast for time period 9 over here, we could average all the numbers, but that's not usually done. Usually we only average the last few numbers, the numbers closest to 9. Well, the number that we select is called the window. If we have a window of 3, then we only average the last 3 values. That number, and that number. 24, 26, and 22. We bring those down here, 24, 26, and 22. We take the average, and then that becomes our forecast with a window of 3. So the moving average, MA3, moving average with a window of 3 or an interval of 3, the forecast is 24. So I will be giving you those windows. We'll be just choosing windows. I'll be giving them to you. Well, use this window, use this window, use this window. Well, we'll be looking at some of the properties of the forecast to where you determine what window to use, but also we'll see some characteristics here on the second pass. What if my window is 5? Well, I take the last 5 numbers, 1, 2, 3, 4, 5. I take all 5 of those down, and then my forecast is 25. Okay, again, a point here is that if you use a moving average technique, what's your forecast? It depends. What's your window? A window of 3 is 24, a window of 5 is 25. You can have different forecasts with the same technique because you have different windows or different parameters. Okay, and you can approach it differently. Okay, introductory example number 2, regression. Okay, again, we have our 5-step process. We have a monthly time series now, and this is aggregated over a month. And again, 8 months worth of data. We plot it, and this time we see the overall nature of this time series is not stationary. It is increasing. It could be increasing or decreasing over time, but in this case, it's increasing over time. So this is referred to as a non-stationary time series. If it's non-stationary, then that decision, that assumption, is you're assuming that non-stationary time series will continue into the future. So that's the pattern that we're capturing, a pattern of increasing, but it's continuing to increase. Okay, then what's the cause of variability? What's a component? Well, a cause of variability around what? Well, let me come up here. Oh, now would be a good time to go back to Canvas and our home here. There we go. And notice down here I say my website. Word files, Excel files, and more. If you click the website, mdharper.com, under Operations Management, down here under Forecasting, I have a lot of videos. Now this video is just a lecture. I'm explaining it. But these videos, notice the introduction is pretty much what I'm doing right now. I have produced it. And so it's not talking, it's a presentation. Okay? And Excel on how to calculate it. We'll do that a little bit today, a lot more next week. Moving averages here, regression, seasonal indexes, decomposition. And notice I have a lot of videos here to go into depth, a presentation on the material. Okay? And so this is a resource that I would recommend you to access to support your learning. And if you understand it, fine. But sometimes this will help your understanding deeper, and so that's going to be important. Okay, good. Let's go back to our problem. Our lecture. Let's go back to the lecture. Okay. The windows here are not calculated. They're given. I'll always give them to you. We won't calculate those here. We won't estimate them in this course. But for regression, we will estimate the parameters of intercept and slope for a regression line. Now, let's go back to components. What are the components? Well, the cause of variability, what does that mean? Well, in the video I talk about it. Let's come up here, insert a shape. Let's do this one, and let's kind of like make it all the way across. Boom, 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 like this. That's pretty level. Let me darken it, make it a little bit thicker, weight, so we can actually see it. That's good enough. Okay, now what do they mean by variability? A component is a cause of variability. We've already defined that. Cause of variability around what? Variability, fine. And this is referred to as a stationary mean. In other words, when you look at all the data, you take the mean of all the data, that's referred to as a stationary mean. What's causing variability around that? Now up here, the variability around this stationary mean is just going to be our stationary average here. The average of all those numbers, whatever it is. Okay. Down here, we're assuming we have a stationary mean. What's causing variability around this? Again, the video explains this quite well. I illustrate it. But here I'm just going to explain it. Well, at the beginning of the time series, the variability is below the stationary mean. At the end of the time series, the variability is above it. What's causing that variability? Below at the beginning, above at the end? It's going to be the actual non-stationary nature of the time series. So the non-stationary nature of a time series is referred to as a trend component. So non-stationarity refers to the time series. The trend refers to the component or cause of variability within the time series. So if that's true, then you say, okay, well then I have a trend component. Well, initially we'll just be looking at linear trends, just linear trends, straight lines. I think next week I might get into nonlinear trends, but this week just linear trends. So let me copy this again. Let's bring this up here and paste this. And now let's come down here and say, okay, well now I know, put one line there, put one line there, say, and actually let's make this shape format. Let's make this, make it dashed. Okay, there's a line, but if we look at this line, notice the data are not exactly on that line. There's variability around the line, around the trend line. Well, the variability around this trend line is unexplained. So that variability is referred to as a random component. So the variability, the cause of variability due to the non-stationary nature of the time series is the trend component. The variability around the trend line is the random component. Now, those of you who have had statistics in 6530 know that variability around a regression line, sometimes referred to as residuals. Well, the random component in this case is the same as residuals or error or deviations. We'll be looking at that today. Okay. The technique of preference is going to be simple linear regression. Now, simple simply means we have simple linear regression and multiple linear regression. Simple linear regression simply means you only have one independent variable and one dependent variable. Well, regression means one dependent variable. You can have more dependent variables. That's no longer regression. That's going to be a different kind of regression. You still regress it, because all regression is a conditional estimate of your dependent variable, and that conditional estimate can be univariate, multivariate, and that gets into mathematical statistics. And the way you do that then becomes multivariate types of issues, and sometimes it's deterministic and sometimes it's non-deterministic, but that's beyond this course. But anyway, simple linear regression. In other words, we're just going to have an intercept and a slope. Like right here, I can bring this down here. We're going to have an intercept down here, and we're going to have a slope of the line through here. And so let's calculate and estimate the intercept and the slope. Well, down here below, I did all the arithmetic on how to do it. And I did this to be complete, because sometimes people say, how would you calculate it? Well, you know, way back when you had statistics at the very beginning, you probably went through these things and some of the squares of errors and this kind of thing. So this is how you would do it. We're not going to do this in here. Instead, what I want to encourage you to use is Excel. We'll use Excel to get the intercept and the slope, and that's the equation for Excel. That's the expression for Excel in the function. So the intercept is a function in Excel, and the slope is a function in Excel. Now, right up front here in the introductory example, let's come back up here and let's just see exactly how to do that. Okay, and so let's take these right here, Control C. Let's bring in Excel. Let me bring this down here like this. So notice I'm bringing in Excel. Let's make this bigger so you can see it. Let me Control V, copy this. And now what I want to do let's back up here. Let's bring this up. I want to do this. Okay, this is going to be equal intercept. And notice it says the y variable. What's my y variable? Y variable is this. So I'll do this, left click and drag, comma, and then it says the known x is the x variable. There's my x's. There they go. Okay, in parentheses, and I press return, and there's 20.75. That's my intercept. Now what's my slope? Equal SLOPE, open parenthesis, the y variables. That's the dependent variable, comma the x variables, the independent variables. In this case, with a time series, the independent variables are time, in parentheses, and there's my 3. Okay, and there you go. So that's how you do it. And that's why this is a lot easier than going through all the mathematics. We could, but they do this for you. So why not use it? Because you know what you're doing. Okay, so there's your intercept and slope. And so you have the intercept and slope times the variable here, whatever your variable is. Let's say if it's 9, I'll put 9 in here, 47.75. That becomes my forecast up here. Okay, so to be complete here, using arithmetic, we can use this. Using Excel, we use this. There's the regression equation with t. There's a forecast equation. I just take y, I'll put an f of t for forecast. And then an example for month 9, we put 9 in there, and there's our forecast. Introductory example number 3. Okay. I'll just back up here. Well, let me do example number 3, then I'll go back to answer these questions on chat. It's a good time to answer questions on chat. Let's see. Forecast of week 10. Good question. For regression, it's simple. You just put 10 in there and do the arithmetic. But what if you had a moving average? Well, once you have a moving average of 24 or 25, depending on whatever window I give you, again, we're not calculating windows in here, I just give them to you, then you take that average with a moving average, and that's your forecast for every time period into the future. Okay, so we don't go back. In this course, we don't use a forecast to forecast a forecast. In other words, if this is 24, so we put a 24 here. If I want the forecast for a week, this is week, for week 10, I don't use the forecast for week 9 and then 8 and 7 for a moving average of 3, a window of 3. I'll use those 3 for everything into the future. So in this course, we only use data to forecast the future. We don't use the forecast to forecast the future. Now, in some applications you do. But in this application of business forecasting, as I'm presenting it, we don't. Okay. Okay, example 3. Seasonal indexes. Now let's go from weekly to monthly. Now we have quarterly time series. Each one of these is a quarter. And I have eight data points. And so therefore I have 2 years worth of data because I have 4 quarters is a year. So I have 8 quarters worth of data. So I plot it down here. Now when I plot it, initially it says, oh, it looks like there's a trend here. It's going up. But it doesn't continue to go up. It goes up and comes back down, and then it goes up again. But this pattern and this pattern seems the same. So when I look at the pattern in the 2 years, both years, I have a pattern that's repeating itself. But it repeats itself on a level, stationary manner. So I would refer to this as a stationary time series because it's not continuing up. It's repeating, but it's repeating in the same stationary manner. So I'd say it's stationary. Okay, choosing your components. Well, first of all, again, like I said before, let's come back up here and make a copy of this, just to make sure I get the right copy. Come down here. Let's put this in here again. What's the cause of variability around some central mean here, right? Something here. Okay, stationary mean. Well, first of all, I can see that it's low here, high here, low here, high here. Again, my video explains this and gives illustrations of it. Here I'm just explaining it. The video presents it. So here I say, okay, what's causing this low, high, low, high? Well, this pattern that repeats. The pattern that repeats. So when you have a pattern that repeats, that's called a cyclical component. A pattern that repeats is called a cyclical component because it's causing variability. Now, when a cyclical component repeats every year, this is 4 quarters, this is quarterly time series. That's 1 year, this is year. When that pattern repeats every year, then that cyclical component is referred to as a seasonal component. So if you have a cyclical component that doesn't repeat every year, it's a cyclical component, but not seasonal. But if you have a cyclical component that repeats every year, it's called a seasonal component, as well as cyclical. Okay, so we have a cyclical seasonal component. So it's seasonal. And so if that's true, then this pattern is going to repeat. But when I look at the first quarter here, 26 is this point here. 24 is the first quarter of year 2, this point here. 26 and 24, they're not the same. But if the pattern repeats, they should be the same, but they're not the same. So what's causing that variability? Well, when I look at quarter 2, they're not the same. Quarter 3, they're not the same. Quarter 4, they're not the same. So if the pattern repeats, it's seasonal. But if they're not exactly the same numbers, there's variability between the years, that's referred to as random because it's unexplained. Okay, the component, the cause of variability within a year is the seasonal or cyclical component. The variability between the years is a random component. And I emphasize that in the videos. Okay, and some people I'm really glad people are showing up. You can ask questions, but at the very beginning I showed my website and I have videos on all this stuff. This will be made into a video, but this is just a lecture. My videos on my website. Maybe more people are here. If I can pull it up. Again, this is my website. If you open Operations Management, come down here. These videos under forecasting, these are not lectures. These are presentations. These are productions. And so I talk about what I'm talking about now in this lecture. But I illustrate it. I bring in captions. I bring in fiction. Well, watch some of them. For example, what am I talking about now? Seasonal index. Here's seasonal indexes part 1 of video 6 and 7 talk about seasonal indexes part 1 and part 2. I go deeper, okay? Okay, finally, the technique is seasonal indexes. Again, let's come back up here. Like I said at the beginning, in our table, when we have a stationary time series with a seasonal and random, then the seasonal index technique is the technique we're going to be using. Let's come down here. 1, 2, 3. Okay. Seasonal indexes. Now, to estimate the parameters, just like we did in moving average, I just gave you the parameters. We didn't estimate them. In time series analysis, you can estimate the parameters or the indexes. Now, you can estimate the indexes, and they're going to be very useful with some applications. But you do not necessarily have to have the indexes to get the forecasts. And I'm going to emphasize that. Because here's an example, a really simple example. We don't need indexes. So estimate your parameters is step 4, but you don't always have to estimate your parameters. If you know what you're doing, you know what you have, you know what you want, you don't need to estimate those parameters on this step. Okay, here's what we're doing. If the difference between 20 on quarter 1 of year 1 and year 2, if that difference is random, how do we remove randomness? When you take random numbers and replace them with a measure of central tendency, like a mean, so that's taking all that variability and replacing it with one number, so you're reducing that variability down to 1. Okay, and actually that's one of the axioms of statistical modeling and statistical analysis is handling variability and error. And you're replacing error and describing error and replacing with something that's predictable. In this case, the mean, central tendency. So the average here is 25. I average each one of these. So I've removed the variability by replacing that with an estimate of 25. I remove the variability by replacing with an estimate of 34. And that's an average, that's a mean. Same with quarter 3 and quarter 4. But then again, that then would become my forecasts. And notice there's no indexes in here. We will do indexes on the second pass through these techniques. But for this time, we don't need them. So there's our forecast. There's our forecast for the next year, 25, 34, 43, and 55. And there they are. Okay? Okay, here we go. Okay, so that's the first pass. And let me reiterate the first pass through this table. I just wanted to define a time series. I want to define stationarity. I want to define components and illustrate it, and a simple application of the technique. And the first pass is the simplest application that I could come up with. It's very, 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 very straightforward. Okay. So here we go. So now the second pass, I'm going to go deeper into moving average, regression, and seasonal indexes. Okay, I'm going deeper. Here we go. Okay, before I get into the detail here, let me come back a little bit. Leslie, for exams, is it a good strategy to pre-build the Excel formulas to put data based on the lessons? No, it's not. The exams are very, very different than the homework. Now, the homework going to be using Excel. For the exams, don't use Excel. My exams are designed for evaluation. I talked about that in the syllabus. And now is a good time to know that. You're not going to be using Excel on exams. Just for the homework and the memos and the quizzes. On the assignments you will, and maybe even on the projects, but not the exams. What is a component? It's a cause. It's a cause of variability. And we have a random component, unexplained variability, a seasonal component, a pattern that repeats, and a trend component, non-stationary time series. Okay, I just went through that. So I said that quickly, but this is being recorded. You can go back and see my explanations, okay? And that's why I like recording this, so you can always go back and look at it again. A component is a cause of variability. Right, Molly. Good job. good. Doesn't hurt to ask them, hey, repetition. Hey, guys, repetition is good. The more you do it, the better you learn it. So I don't mind. Hey, I don't mind these questions. I covered that. I don't mind saying it again. Repetition is good. Okay. Okay, now the second pass, let's go deeper. Moving average. Now, I'm going to talk about the simplicity of moving average and the complexity of moving average. Here we go. And the sophistication and the power of moving average. How simple it is and how powerful it is. Here we go. Let's go back to the weekly time series. There's two of them here. I mean, there's one of them. Here's the time series here. And I plotted the time series down here. There's my x's. Up and down, up and down, up and down. Okay. Now, I'm going to apply a 3-point moving average, MA3. Moving average with a window of 3, interval of 3. All that means is I take any three numbers. Let's say these first three numbers. I average those three numbers. And the simplicity of moving averages is whatever that average is, that's the forecast in the very next time period. So the average of those three numbers is the forecast for time period 24, or time period 4, which is 24. I can take any three numbers, like these three numbers. I average those three numbers together. That average is the forecast of the very next time period 8, again 24. If I take 7, 8, 9, that average is the forecast for time period 10 or 27. Now, if I want to forecast time period 13, I don't have data for it. Then I take, since my moving average, since my window is 3, I take the last three values, and the forecast for MA3 is going to be 24. Now, one thing about how this is simple, but be careful. You only take the last three. You do not take 3 in the middle. You don't take 3 in the beginning. You don't take 3 spread out through the time series. You take the last 3 values in that time series, because a time series has a timestamp. You take the very last 3, and we will revisit that here in a minute. Sometimes it's subtle, but always remember that definition. If my moving average is 5, I take the last 5. 1, 2, 3, 4, 5. So it's 25.6. Okay. So if I take these 5, 1, 2, 3, 4, 5, if I average those 5 numbers, that's the forecast for time period for the MA5 for time period 5, which is 26. Okay. So I took MA3 and plotted. That's the squares here. Bing, 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 bing. So that's pretty much the simplicity. Okay. Actually, Craig, yeah, this is a good question to address right now. A great time to, in this example, period 14 and 15 would be the same as 13. Yes, it would. When you're using a moving average for this course, what a moving average does, remember, I mentioned before, conceptually and mathematically, philosophically, you take variability and you reduce it and replace it with a number, and that mean is the estimate of reducing that variability to one number. Well, you do the same thing. Let me see if I still have my. Yep, it's still there. The same thing with my stationary mean. Let's put it like right here. You have the same thing with a stationary mean. Once you have estimated it with an MA3 or MA5, that forecast is the estimate of your stationary mean, and that's going to be the same for every data point into the future. Okay, and that's the philosophy and approach that we're taking in this course. Okay, now some applications have different philosophical axioms, and they go a little different direction. But the basic fundamental business forecasting uses these definitions, and that's what I'm using. Okay, very good. Now that's the simplicity of moving average. Now let's look at the power of moving average. I'll talk about the power looking at 3 different characteristics, and the first characteristic is called impulse response. Impulse response. Okay, I'm taking a different time series here. It goes 25, 25, 25, and between time periods 6 and 7 it jumps to 55. So down here, here's my 25, 25, 25, then it jumps up to 65. Now that jump in my time series, that step function, that impulse, anytime you have a change in the time series that's important, you want to model, you want to follow, it's referred to as an impulse. So in business forecasting, it's called impulses, and sometimes referred to as signals. Like if this was a sound, that would be a single. Bop, that's a signal, okay? Because sound is a physical wave. Okay. So down here, I apply a 3-point moving average. Well, 25, 25, 25. Let me reduce this down so I can do both the table and the graph. 25, 25, 25 is just 25. Okay. 25, 25, 25 here, 2, 3, and 4 is just 25. 25. But when I come to 25, 25, 55, let me reduce this down a little more. There we go. 25, 25, 55, the average is 35, adjusted 25 to 35. So time period 8 is 35. Time period 8, my MA3, which is a square, jumps up to 35. And then 25, 55, 55, the average is 45 here. It jumps up to 45. And finally, when I get to all 355, it's going to be 55. So notice what happened with the MA3. My time series had an impulse, went from 25 to 55. It jumped. Boom. Step function. Now my MA3 responded to it, but after that impulse happened, it took 1, 2, 3 time periods before it responded to it. That's called response time. And since you're responding to an impulse, that's referred to as the impulse response of a moving average of the window of 3. Well, notice the window is the response time. So if I have an MA5, what's the response time? 5. So once that impulse happens in the time series, the response time for MA5 is going to be 5. Is it? Yes. So here, and here's my MA5 here, and it goes, once the impulse happens, it goes 1, 2, 3, 4, 5. Called response time. So if I want to respond faster to an impulse, the moving average window would be decreased. So decreasing the window will respond faster to an impulse. Well, that's called an enhanced impulse response. You're enhancing your impulse response because you're responding faster. Okay? And why would anyone want to do that in time series? Well, the difference between your time series, your X's, and your forecast down here, here's your time series, here's your forecasts. Now remember, your forecasts are driving your operations. Well, if your demand is up here, suppose our time series is demand. Our demand is up here. This is how many customers that are actually coming through the door for us to service. Our forecast was down here. Here's how many servers we have. This difference is bias. And that bias means you're not meeting your demand. You're not servicing your customers. You're losing sales. So that bias is not good. You want to respond to that as fast as possible to eliminate that bias, because if this is what your demand is, here's what your resources, here's where your resources should be to meet that demand. So reducing the bias by decreasing your window will respond faster to an impulse. So there's one characteristic. One characteristic. Now, the second characteristic is called noise dampening. Okay, this is interesting. And we'll see this more next week too, next Tuesday. Here I have a different time series. And this time series, my X is down here. And this time, notice it go up and down, up and down, up and down, up and down. Now, each time a time series changes, if that's important to me, it's an impulse. But if it's not important to me, then that's just a random component. It's just random error. The random error in a time series referred to as noise. Now the random is the component, cause of variability, unexplained. Noise is referring to the time series. The time series has noise or volatility. It's variable, okay? But that variability is unexplained. Well, volatility means there is volatility. It could be explained and it could be unexplained. Unexplained is random. Explained, there's where you have systematic type measures like regression. Anyway, we'll do that later. It may go much deeper in another course. The idea here is that this is just a random component. Well, I'm going to take an MA3 and MA5 and apply to this, and there it is. I don't know why these aren't equal. I'll make them equal. There we go. Now, what I did here, my MA3 is my squares. Here, my axis is my time series. My square is my MA3. My triangle is my MA5. Now, to illustrate this characteristic, let me throw some terminology here. Let me describe what we have. Notice the time series has a minimum of 21 and a maximum up here of 25. So the minimum to the maximum is 21 to 25. That min to max, that difference is the amplitude or magnitude of my time series. And so the magnitude is important. If this was a sound wave, and I mentioned a sound wave is a physical wave, okay, over time, it's a time series. That if from the minimum to the max, if that increases in size, instead of 21 to 25, if that was 11 to 55, okay, it's increasing. If that's a sound wave, then that's the same thing as the volume increasing. So if I look at the max to min here, the magnitude, the interval, the amplitude of my sound wave, if it goes down, then I'm just talking very, very soft. If it goes up, then I start talking much louder. Got into red. That was my drama. You can remember that. Well, in business, when you have a large magnitude in your demand, that's going to wreak havoc in your operations. And you have to be very, very careful of that. But is it explained or is it random? What's the cause? If it's random, then it's just noise. Well, what happens to the noise? Well, my MA3 here, the minimum is 22, the maximum is 24. So my time series goes from 21 to 25. My MA3 goes from 22 to 24. My MA5 goes even, the range is even less. So notice what's happening. As my window increases, then the time series of my moving average decreases. The amplitude decreases. Decreasing the amplitude of a time series is referred to as dampening. Dampening a time series, but if the time series is noise, you're dampening the noise. You dampen the noise. Now, how is this used? So increasing the window will dampen the noise more. And so that's called enhanced noise dampening. So a larger window has an enhanced noise dampening. Now, theoretically, MA5, how many time periods do we have? We have 12 time periods here. What if my moving average was 12? We average all 12 numbers. Then what's going to be my time series? It's going to be one number, a flat line. How much variability is there in a flat line? Flat line, 0. So I've taken that variability and replaced it. I've removed all of it. So as my window approaches 12, I've removed all the variability in this time series. So theoretically, when you have a time series that goes infinity, then if your moving average is infinity, then you know exactly what that stationary mean is. And that's theoretical. Okay. When is this used? Well, again, if you're using your forecasts, and you use your forecast to monitor and to run your operations, well, if the demand goes up and your forecast goes up, you hire people. Go down, fire people, hire people. Well, if you try to using these forecasts to run your operations, that volatility in your forecast, it's hard to know what to do. And so, if it goes up, it's going to come down. If it goes down, it's going to come up. So maybe we should just dampen this out to see what some kind of a reasonable level is. So to stabilize those forecasts, increase your window to dampen the noise of your time series, to stabilize your forecast and stabilize your operations. So now you pretty much know what you're going to be doing. Okay. That's the second one. The third one is filtering. Okay, now I have a third time series. Here, 21, 22, 26, 21, 22, 26, 21, 22. Every three, you probably noticed this, every three are the same numbers. 21, 22, 26. 21, 22, 26. 21, 22. I keep doing that. Boom, 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 boom. So now, I apply a 3-point moving average, and there's my squares. Now, again, let me describe what I have here and what I'm doing. Remember, back when we talked about we have a pattern that repeats, and we do, if the pattern repeats every year, it's called a seasonal component. If the pattern repeats something other than a year, it's called a cyclical component. Well, if a pattern repeats, it's cyclical. But if the pattern's a year, that cyclical is a seasonal. Okay? But one more terminology. The number of points in that pattern is called the periodicity of the component. The periodicity of the component. Let me, periodicity. The periodicity of the component. Let me make that larger so you can actually see it. Bold. Boom. Let's make it 20. Okay. The periodicity of a cyclical component is the number of points that are in the pattern. So here's the pattern. How many points in this pattern? There's 3. 1, 2, 3. So that pattern repeats. So every 3 points it repeats. That's the periodicity. Now I applied a 3-point moving average. But when I applied it, I averaged those 3 numbers. Now notice how I said that. I said that very carefully. I said I applied a 3-point moving average. But I didn't say it's a forecast. Actually, I didn't apply it as a forecast. I applied it as a filtering tool. If it's forecast, then the average of those 3 numbers is the forecast for time period 4. If it's a filtering tool, I'll average those 3 numbers and apply that to the middle of the interval. So that 23 right there is the average of those 3. And then I move to the next 3, and it's that. So if I'm using moving averages as a forecasting tool, that averages the forecast for the very next time period. If I'm using it as a filtering tool, then that average is the average of the middle of that interval. That's what I'm doing. So that's why it starts here, the middle of this interval. So notice what I have here. I have a time series with a cyclical component with a periodicity of 3. I apply a 3-point moving average, and I have a time series where that cyclical component is gone. It's removed. That's called filtering. You filter out that component, it's removed. How did I do that? You're going to filter out a cyclical component when the window of your moving average equals the periodicity of the component. When the window equals a periodicity, then you will be filtering out that component. So how is this used? Well, and we'll see that today when we start putting all this together. I'll do regression, seasonal indexes, then I'll put everything together. But the filtering is where you start decomposing a time series. So notice this time series here has a stationary mean, and it has a cyclical component. So when you look at this time series, what's the stationary mean? Well, if you filter out the cyclical component, what emerges is the stationary mean. Now I know what it is. In this case, it's 23. Now what if there's a trend line? And we'll see that in a minute. Well, when there's a trend line and there's a seasonal component or cyclical component, you don't know what the trend is until you filter out the seasonal component with a moving average, and then we can see what the trend line looks like, and we can forecast that into the future. So we'll use this in decomposing a time series, which is a very common process in business. And that's why I'm taking time to develop it one step at a time. Okay. So let's go on. Before I continue on Okay, let's back up. That's just moving average. So I'm going to do regression, seasonal index, then I'll go back to exponential smoothing. But before I go on to regression, let me take this as an opportunity to deviate just a little bit and talk about forecast accuracy. 2-7, forecast accuracy. In other words, you have a forecast. How good is it? Oh, Sridevi, you're right. You're absolutely right. I understand we were talking here about forecasting. At the same time, I remember using these same techniques in digital signal forecasting for noise cancellation and filtering. Absolutely right. What I'm doing is showing you a very simple introduction to digital signal processing. But notice it's digital signal. Digital. And you probably did spectral analysis with Fourier transforms. If you're probably an engineer. And before it was digital, it was analog signal processing. We did that way back then, and that's pretty much where I started. So everything is connected. Everything is connected. You say, oh, well, I was an engineer. Oh, I was a liberal arts major. Oh, I was a history major. Oh, everything's connected. Everything is connected. I don't care where you came from. Everything's going to be used no matter where you are. I'm a music major. That can be used. Okay. Anyway, don't get me onto that. I have a definite feeling about that. Whatever your background is important as far as I'm concerned. But you're right, Sridevi. This is digital signal processing in business at a very introductory level. Okay. And when I say decompose a time series using moving average, well, that moving average can be expanded to a transform. And that transform would be a Fourier transform with digital signal processing and a Laplace transform for analog signal processing. And then you have a Z transform and all kinds of things. It depends on your time series. And some of the times, your time series, instead of univariate, is multivariate. And it's surfaces and time and everything. Okay, that's not this course. You're welcome. Okay, how good is a forecast? Now let's get back to business. How good is business is so valuable, so practical. How good is a forecast? Oh, my forecast is 100 items next quarter. Well, how good is it? Before I get into Leslie, yes, it's in Canvas. I posted these notes are in Canvas for everyone who came in late. It's on Canvas. You can get on Canvas and this is the word file I'm using in Canvas. Good. So how good is it? Is it good? If it's bad, be careful using forecast. Again, mistakes that are made. They go, oh, it's a mathematical forecast. It may not be that good. Okay, it may be really good. How can you tell? Well, there's a lot of different measures of forecast accuracy. I'm using these three: mean deviation, absolute deviation, and tracking signal, because these illustrate how forecast accuracy techniques are used very effectively. Okay, here we go. Assume a window of 3. Assume we have this time series. And let's assume we're using a forecasting technique with a moving average of the window of 3. So I average these 3, and that's my forecast. And I do the same thing all the way down. Now I want to forecast time period 13, which is 24. So my question is, what we're addressing here is how good is that forecast of 24? How good is that? How much error is in that? 24 plus or minus 1/2, 24 plus or minus 5, 24 plus or minus 20? Good question. We better know how accurate that is before we place decisions in operations moving forward, or we can have bigger problems by using forecasting if we didn't. So how accurate is it? Well, we're using a concept here saying, well, how close is this forecast to the actual data? We don't have the data, but we don't have the observation in time period 13, but we do in the past. So how close did the forecast come to estimating the data in the past? Well, the closer the forecast F is to the demand data D, the closer the F's and D's are together, then we'll use that as an argument to infer, like, well, the better it's going to be in the future. There's no reason not to think that. Well, how do we measure that? We take the difference. D minus F, D minus F, D minus F. So this is the difference. Now this difference has a lot of names. You have a demand and you have a forecast, an observed value and an estimated value. That difference is called difference, called deviation. Here it's called deviation. It's also called error. It's called bias. It's called residuals. It's called all kinds of things. But that's a concept, a primary, fundamental concept of statistics. An observed data and an estimated value. And what's the difference? Now, again, we could use all of them, but we're not going to. And some textbook says use everything. That's fine. Nothing wrong with that. But in this course, to illustrate, you don't have to do that. Instead, I'm going to assume a window of 4 for the forecast accuracy measures. All that means is I'm going to take these last 4 numbers and use these. Okay, if you don't, I'm into this, but let me just really quick to show you real quick, Leslie. I hope everyone doesn't mind this. Boom. Come to here. If you come back here to Canvas, the home, come down to weeks 2 and 3, and then in week 2 and 3, look under videos. And there's the forecasting. Download the Word file right there. There it is. There we go. You got it. So that didn't take too long. Make sure everyone's on board. Okay, window of 4. I'm taking these last 4 deviations. Let's come back to this. Okay, so let me take these 4 down. And so now, the first thing I'm going to do with these deviations, I took these 4 down to right there, is I'm going to sum them, divide by 4, and take an average. And then you'll see a mean deviation with a window of 4 for my forecast accuracy measures. And there it is. Okay, so how do you interpret that? Well, notice I'm taking an average of sample size of 4. I'm taking the average, the minus sign is in front of the F. There's a minus sign in front of this average. Well, the minus sign is in front of the F. So on the average, the forecast is larger than the average data in those 4 data points. The forecast is like, well, that difference between the average forecast and the average data is going to be bias. So a mean deviation is a measure of bias. Okay. Well, it's a minus 1.25 mean deviation. That's how much bias you have. Well, is that a lot? Is that a little? How do we interpret that? Well, a brute force way of doing it is looking at the magnitude of the numbers. I see here that I have the magnitude of these numbers is 26, 19, 27, 26. Well, minus 1 is about 5% of the numbers. Okay, let's see here. I want the mean. So this is the mean. Taking a mean, you take a sum and divide by the number in the sum. That's how you take a mean. Mean is an average, it means the same thing. So this is like 5%. 5% of the magnitude of these numbers. 1 is about 5%. 10% is 2, and 5% is 1. So that's not small, but it's not large. It's kind of like in the gray area. It's not bad. So our bias here is not that bad. Okay, but then we go to the mean absolute deviation. Okay, we take the absolute value of these. Simply take away the minus sign, and then we take the average. 3.25. So this is the mean of the absolute deviations for a window of 4. So let's interpret this. Well, the way we interpret the MAD, or the mean absolute deviation, is let me illustrate with 2 different time series. Again, I do this in the video. And actually, this will be a video as well. And a lot of people asking questions. If you came in late, don't worry. This will be rendered as a video, and it'll be posted on Canvas. And you can see this, and you go back and watch this over and over again. And that's why I'm kind of going fast, because I don't want to go slow, because it'll take too long. You can go back and listen to it over and over again and ask me about it during office hours. 2 time series. Now this time series, my deviations here, let's say, was a +1 minus, I'm taking two, sorry. This time series over here, +1, -1, +1, -1. The pluses and minuses average out. So my bias here, my mean deviation is going to be 0. Well, you can't get any better than that. That's perfect. The forecast in the time series, the averages are perfect, 0, no bias. So my forecasts are right on target with my data. Over here, but if you take the absolute value of plus and minus ones, they all become +1. The average is 1. Time series 2 over here, let's take a deviation of +100, -100, +100, -100. Again, the pluses and minuses average out. They both have 0 bias. Both are perfect as far as bias is concerned. But when you take the absolute value, the -100s become +100s, and the MAD, the mean absolute deviation, is 100. What's the difference? Well, they both have no bias, no problem. But over here, the variability around that 0 bias is 1. Over here, the variability around that 0 bias is 100. Which one has a greater risk of, let's say the forecast is 24, which one has a greater risk of being far removed from 24, our observation? Well, as the MAD gets larger, the risk of not being close to 24 increases. Okay? In other words, if I have a small variability, then I'm going to get something very close to 24. If my MAD gets larger, I'm going to get something far removed from 24. Okay? Well, the magnitude is 3.25. That's not bad again. Okay, 3 is maybe a little, maybe 15%. So that's not too bad. Plus or minus 15%, that's not bad at all. It's not. It could be better, but it could be a lot worse. So this is not bad. But now, this is called the measure of variability. And sometimes that's used as risk. The third is the tracking signal. Now, the tracking signal is a combination of the mean deviation and the MAD in a very special way. So I take the numerator, the sum of the deviations, which is -5. I divide by MAD with 3.25, and I get minus 1.53846. Now let me interpret this. Here we go. Since the numerator is the sum of the deviations, and the deviation is a measure of bias, the tracking signal is also a measure of bias, but it's a different kind of bias. The tracking signal is a measure of relative bias, whereas the mean deviation is a measure of absolute bias. Let me illustrate the difference with an example. Let's suppose over here, well, we do have a time series of 26, 19, 27, 26. The mean deviation is minus 1.25, and the tracking signal is minus 1.53846. Okay, good, we have that. Now, what if our time series was 26 million, 19 million, 27 million, 26 million? If these numbers were in the millions, then our mean deviation would be minus 1.25 million. It'll be a huge bias, because that bias is absolute relative to the magnitude of the time series. But the tracking signal would still be just minus 1.53846. It's a relative bias. Relative to what? Not the magnitude of the time series, relative to, here it comes, the window. It's relative to plus or minus 4. So the tracking signal, no matter the magnitude of the time series, the tracking signal is relative to a plus or minus value of whatever the window is. If the window is 4, it goes between plus or minus 4. 0 is perfect, no bias. But as it gets closer and closer to 4, or closer and closer to minus 4, as the magnitude gets closer and closer to 4, the bias begins to increase in significance. So the mean deviation tells you what the actual bias is. But the tracking signal tells you if that absolute bias is significant or not. Now notice between 0 and minus 4, we have a minus 1.53846. Again, 2 is in the middle, 1 is low. again, it's kind of like in the gray area. It's not bad. There's variability in there. But if it was in the 3s, that's not a good bias. That we have a lot of bias in our forecast. If it's less than 1, it's pretty level. It's a pretty strong forecast. Okay. Now, for example, here's how it's used in a memo or a report. Suppose you are going to forecast a different problem over here, and someone says, our mean deviation was, we're looking at budgets, and the mean deviation, there's a $100 bias in the past. We have $100 in our bias. Our mean deviation is $100. And we looked at the past data. Well, is $100 significant or what? I don't know. Well, what's the actual dollar values of the budget? Well, if our dollar value was 200, 250, 150, $150, and if our bias was $100, that's a lot. A $100 bias is pretty large when the actual time series is in the 100, 200, 300, right? Because that bias says, oh, okay, it's 100, but it could be 0, it could be 300 or 200. But in that case, the tracking signal will be very, very close to the window, like a 3.9. But if our time series was in the billions, okay, we had a 3 billion, 5 billion, 4 billion. Is $100 significant? No. And the tracking signal in that case would be like really close to 0.00001. So the point is, the mean deviation tells you what the bias is. And you can interpret it relative to the magnitude of the time series. But the tracking signal tells you this is if that bias is significant or not as it gets closer in magnitude to the window. And we're going to use that later with exponential smoothing, with artificial intelligence and forecasting to actually adaptive forecasting. Okay, so going a little bit, so that's the explanation for that. Okay, here I'm showing you what it looks like in a graph. And here's my data. It's beginning to increase. And so here's the deviation increases. Well, that deviation should be seen in the moving average, and it is 3, 5, 6, 7, 8, 11. I'm just showing you what it looks like in a graph up here and what it looks like in a table. That's the deviation bias increases. Now, what about the variability? Well, here I have a time series that keeps increasing in variability, like that, boom, boom, boom. Well, we should see that in the MAD, and we do. In the MAD, 4, 7, 10, 15, 18, 24. That's what it looks like in a time series. This is what it looks like in the table. Okay? So just to show you, get a good feel for what's happening. Okay. Okay, now let's go to the next technique in regression. I think everyone in this course, I think most people have had statistics. 6530 is data analysis. You've had a little bit of statistics or regression in there, or maybe in other courses or whatever. So we're using regression, but let me show you how this can be applied in operations. I'm hoping people had regression, because then I won't go back and reteach it, but I'll refer to it. And when people learn it, they have a wrong implication that there's only one type of regression. There's a lot of types of regressions. Okay. You got all different kind of assumptions. Anyway, so now let's start with an additive model. Extrinsic forecasting. Remember, extrinsic is causal forecasting. All that means is we have a leading indicator of something outside the time series forecasting the time series. For example, suppose we want to forecast carpet sales in an area of a metropolitan area. And we've noticed the past 6 seasons that at the beginning of the building season, the housing permits are correlated with carpet sales. So we have the housing permits before the building season, and the building season is where we have the carpet sales. So we go back to 6 seasons and say, I know, let's pull off a paired for the different seasons, how many housing permits were at the beginning of the season, and then that resulted in how many carpet sales. So we have 6 pieces of data, 6 paired pieces of data. 2, 3, 4, 5, 6. Okay. So we say, okay, well, let's use this to forecast carpet sales because we're selling carpet. Okay. Now, I'm taking this as an opportunity. Sridevi, you talked about digital signal processing. I'm taking this as an opportunity to introduce, for those who you don't know that, I'm going to introduce something called a transformation. You take the data and you transform it into a different form that's easier to use. Very common technique in mathematics, and that technique in mathematics is used all the time in different disciplines. Okay, but I'm simplifying it a lot. My transformation, the operator is division. So I'm going to transform carpet sales to a y variable. And that y variable, the transformation from carpet sales to the y variable is dividing by 1,000. So 3,000 becomes 3. So this is 3,000 square yards. This is an x value of 3. So all I'm doing is transforming it using division. Now this might seem trivial, but it's not. That process is significant in some applications. I'm transforming housing permits to the x variable by dividing by 10, and so those become 2, 4, 4, 5, 6, 8. I take the x and y, I plot them, and there they are. And I see that as my x increases, my y increases. I can use that relationship, capture it, and then say whatever the housing permits are, I can use that variable, which is extrinsic, which is causal. I can use that variable, whatever it is, pass it through this line and estimate what my carpet sales are going to be. And then I can plan accordingly. Okay? So the way you do that is you take your, down here's again the calculations of regression, but notice what I'm going to be doing in here and encourage you to do, which I've already said, again, is using the slope and intercept. We've already done that. There's a regression equation. There's a regression equation, and there's the example. Okay. Well, notice right here, I've already done this. The regression, I just rounded this up to 2. I rounded this down to 1. But you know, since I'm here and we have time, I think this is important. Let me show you, let me deviate a little bit from school. And because this is a professional school, it's a business school. We are preparing people to understand these concepts and techniques and how to apply them. But if some of you work, I know, and you know when you start working, it's very different than what you do in school, of course. And I've done a lot of things outside of school before I came into university. I did research. I was a VP. I did consulting. I did a bunch of stuff. And I ran a company. I had a company. But the thing of it is that if you're doing regression, you look at this thing. Here's how you would do it. And by the way, I've done this quite back when I was in research. I would used to do this all the time. I was the resident statistician because one of my degrees is statistics. And they go, hey, Mike, could you do this? Yeah, sure, I'll do it. And so they gave me this data. And if the data looks as fairly consistent, the variability is not that great. I says, yeah, I'll get a regression line. But let me tell you, they come in your office, can you do this? I look at it, I plot the data, I look at it, go, I'll see what I can do. Make sure they leave your office and don't let them see what you're getting ready to do. You plot the thing, you take a line, and you say, I'm going to put a line through this thing. I'm just going to eyeball a line through it. This looks pretty good. Let me do this. Let me put this over here like this. That goes through the data pretty good. That's not bad. That's going to be good enough for government work. And I was working for the government. They don't know. What's the intercept? 2. What's the slope? Well, this is 0, 2. This goes through 8, 10. I mean, that was convenient. So from 0 to 8, the x increase is 8. From 2 to 10, that goes up 8. 8 over 8, the slope is 1. Okay? So I got it 2, 1. See how fast that was? That's about how fast I did it. I don't tell you how many times I did that when I was in government. And you wait 2 or 3 days before you tell them. Right? Because then you say, you see you in the hall. Hey, Mike, have you done it? It says, oh, I think I might have something for you. And so you give them this 2-in-1. Oh, that was simple. Yeah, I tried to simplify. So I tried to simplify as much as I could for you, but I think I got something. You know, the person last time it took forever. They never gave me anything. Says, oh yeah, well I worked hard for you. But the point is, job security. The point is, understand that this will work because the variability is relatively small, and you know that if you did least squares, if you did a regression, it's going to be very close to this. And the error, since it's forecasting, really just doesn't matter. If it matters that much, then probably you shouldn't be doing forecasting on a regression anyway. You should be modeling it with much more detailed modeling. So understand the problem before you work it and only apply the data. So that's industry and that's real life. In this course, do least squares regression. So I'm telling you what not to do in this course, but when you start working, that's what you do. In this course, I'm going to ask for the slope and the intercept from Excel. These are least squares. Okay. As I say, least squares is only one definition of. There's different definitions of least squares too. You can least squares on the dependent variable, least squares on the independent, least squares on both, least squares of errors, least squares of volumes. You can do all kinds of stuff. Okay. Anyway, let's go on. Oh, and then I do the same thing with a time series. Okay, where the x variable is time. Okay, now seasonal indexes. Okay, this is the last thing. We'll put it all together. Then exponential smoothing, then we're done. Okay, now in this one, I take 12 quarters of data and I plot them. And like I said before, there's a 4 quarters. That's a year. That's a year. That's a year. I have a pattern that repeats. The periodicity is 4. Okay, before I get into this, let's see. So we compute the bias and all these parameters after we get the real data. Be aware of what the bias is. If there's a large amount of bias, then that just alerts you on how to use your forecasts. Don't put a lot of trust. Don't put significant decisions in your forecast if there's a large bias. If it's relatively small, if the tracking signal is close to 0, then you can put more trust in your forecast. All this is doing is talking about how much do you trust and how strong should your decisions be. If you have a lot of bias, you might want to try sampling more, using a different analysis, or trying to sharpen things up, or trying to make decisions that are more robust and have an exit strategy. Let's see here. What was the purpose of transformation? Transformation is taking a problem, transforming it in a form that's easier to work, easier to solve. Okay, that's the purpose. A real quick story. I don't want to stay here too long, but this is important. Craig, you're right. Makes the data easier to understand, but also the solution easier, and also easier to represent, to present. Years ago, one of my children was in school in like I think it was like AP Stat or something, and they brought home this extra credit. Says, "Hey, Dad, will you do this extra credit for me?" Who's it for? For school? Oh yeah, sure. It's just high school. I'll do it for you. So I worked. It was like 9, like a 3x3. 9. I worked him, gave it to him. He turned it in for extra credit. It's high school. It doesn't matter. So I gave it to him. He turned it in. He came home and he says, "How was it?" He goes, "Well, they're all right, weren't they?" "Oh yeah, they were right. But the teacher asked me a question. She said, 'Oh, how did you do it?' And he said, 'I didn't know.' I said, 'I'll get back with you. Can I talk to you? I'm busy, but let me get back with you.' And so he says, 'Oh, okay.' So the next time he brought one home, I worked the problem. I worked him. But then I worked him again to explain to him how to get the answers. So getting an answer and explaining how to get the answer are two different things. So I explained to him, and by transforming in such a way, okay, if you look at it this way, you can see that's what the answer is. Now, you may not get the answer that way, but you can illustrate it that way. Oh, I see. So he had 2 or 3 of those through the year, at the end of the year, and I says, how'd it go? Fine. And so, and she says, the last extra credit, I kept doing that for him. And he started doing it himself. He learned by taking a problem, looking at it a different way, and then solving it, transforming it. I see it. And then they say, oh, I see. And she says, you have a really weird way of looking at things. The teacher told him that. You have a really weird way of looking at things. And I thought, yeah, that's true. It's practical. It's practical. Unfortunately, the theory is important to understand the concepts. It's not necessarily necessary to use the theory and these techniques to get an answer, as long as you understand that your practical solution is just as good. Okay, let's go on. Okay, so when you know you have a seasonal component, then what we can do is, like we did before in the introductory example, put year 1 here, year 2, and year 3. This is called blocking the data. I'm going to block it out. Blocking means I want quarter 1 is all blocked together because the seasonal component is the same for the first quarter of every year. So I've blocked it to put all the seasonal contribution together in one column. The contribution in the second quarter is all together there in the third quarter and the fourth quarter. Okay, so I have a stationary time series. You can see here it's stationary. So therefore, my average then becomes my forecast. So that was my introductory example. Now let's go deeper. So let's go a little bit deeper. Well, if I take the average of my forecast here, my average is 30. So let's interpret that 30. Well, notice that my time series has a periodicity of 4. My time series has a component, and the component, which is seasonal, has a periodicity of 4. So there's 4 points in a pattern. So if I want to filter that component, I want to apply a moving average of 4. Because if the periodicity is 4, the moving average is 4, then it's going to cancel out and filter out the component. But that periodicity also applies, bringing the forecast down, it also applies to the forecast. So these are my forecasts, but the seasonality are in those forecasts. So if I apply a 4-point moving average to the forecast, essentially what I'm doing is filtering out the seasonal component. If I filter it out, that 30 then is the seasonal contribution removed or filtered. So that 30 then becomes my forecast without the seasonality. It's called seasonally adjusted forecast. Seasonally adjusted means you remove the seasonality. You adjust it out. You remove it. And so these are the forecast with seasonality. These are the forecast without seasonality. Seasonally adjusted. Because I've averaged them, I filtered it, and what emerges is what is left after seasonality. So these don't have, but notice they're constant, 30, 30, 30, 30, which means I have a stationary time series, and that 30 then is the estimate of the stationary mean in this time series. 30, 30, 30, 30. Okay? Now I can compare these two. I can compare the seasonal versus the seasonally adjusted. Well, in quarter 1, ask the question, what's the contribution of seasonality in the first quarter of every year relative to the seasonally adjusted? Well, when you don't have seasonality, and you do have seasonality, the seasonality will increase it. In this case, it increases it by 9. Or I can express that as an index. 39 divided by 30 is 1.3. Or I can say the first quarter of every year is really a 30% increase above the seasonally adjusted or the forecast with no seasonality. It's a 30% increase above the seasonally adjusted forecast. So for the second quarter, it's a 60% increase. For the third quarter, oh, look, the seasonal is below, okay? So it's 0.9. It's a 10% decrease. And this is an 80% decrease. So these are called seasonal indexes, SI. So notice how I derived this or described it, where the seasonal forecast is the seasonally adjusted times the index. or the seasonal value is the seasonally adjusted value times index. So I did it with a forecast. You could also do it with the values. I can come back up here and do it with my actual time series, the values, because these values have seasonality in them as well. And I can seasonally adjust the values just as well as I can seasonally adjust the forecast. So notice the equation. I'm taking the seasonal value, I'm abbreviating it SV, seasonally adjusted value, abbreviated SAV, seasonal index, SI. So there's my equation, there's 3 numbers. Now in the homework, you'll be using this equation all the time. And sometimes it's going to be word problems, definitions, put numbers in there. And you'll see it you'll see it in the exam too. So here's an example of an exam question. If the seasonal value is this, seasonal index is this, what's the seasonally adjusted value? Well, you're gonna divide. Okay, divide the seasonal value by the seasonal index. So the way I like to see this, here's the way I like to remember this. And forgive me if this is too elementary, but this is how I think. It's easy to have these mnemonics. You have, if seasonal value, say this is a value with seasonality in it. So this is a seasonal. If I take seasonality out, then that's my seasonally adjusted value. If I want to put seasonality into a number, I'll multiply it to put seasonality in. So I multiply it to give me a seasonal value. If I want to take seasonality out, I'll divide it to take seasonality out. I just always think of that. I multiply to put it in. I divide to take it out. Put it in, take it out. That's how I think of it. And it's kind of elementary, but sometimes I think in a very elementary sometimes. It's easy to remember. It's easy for me to remember things if they're simple. I try to simplify. Okay, so now, how can these indexes be used? A lot of different ways. Let me illustrate 3 applications down here. Before I get into this, let's do the questions again. For the signal, is there a general cutoff relative to the window that would usually be used to determine whether something is overly biased? How p-value works. Tyler, yeah, there is. And as far as the is there a general cutoff relative to the window percentage that usually would be determined whether something is overly biased? Yeah, and we'll talk about that with exponential smoothing. I'll talk about that here soon. Very, very interesting way how people, very ingenious ways, have people come off these cutoffs like you're talking about. So they absolutely do. And there's a lot of different ways. I'll talk about a few very clever ways when I get into exponential smoothing. So we will revisit this. So I'm glad you brought it up because we will revisit this later. Okay, 3 applications. I hope that's okay. I'll reserve that to later. 3 applications. Application number 1. You're in a meeting. You're sitting at this meeting and say, they make an announcement, and you're in operations, right? You make an announcement. They say, next year's annual forecast is 400. What are your seasonally, so take that 400 and adjust your operations according to your seasonal forecast. And you look at this and go, wait a minute, 400? Annual forecast is 400? Wait a minute. Let's back up. For the past 3 years, we've had 30, 30, 30, 30. So my annual forecast at 30, 60, 90 is 120. It's 120, 120, 120 is pretty much what I have here. Okay. So where does 400 come from? Where'd it go from 120 to 400? Because my annual forecast was 120 for the last 3 years. Oh, forgot to tell you. You're right. Well, we've acquired 3 new regions, and so all of a sudden we are supplying 3 regions. Oh my goodness, really? He says, yeah. Well, your budget's going to go up, so you can hire more people, but you have to adjust your seasonal forecast to know how to manage your operations. So what are they? Aha. Okay, well, this is not too hard if you know forecasting. So the seasonally adjusted forecast then, it's 400 for the year. What's it for every quarter? Well, the seasonally adjusted quarterly forecast is 100. If it's 400 for the year, you divide by 4 to get 100 every quarter. 100, 100, 100, 100 is 400. But that's my seasonally adjusted over here. What's my seasonal? I take my indexes, I multiply them to put seasonality in, and my seasonal forecast then is 130, 160, 90, and 20. So I know at the first half of the year, I'm going to have to hire people pretty quickly. I'm going to have a large demand, and I'm going to have to address this very quickly. The last half of the year, it's going to be less demand because it's just how the indexes fall out. And usually these indexes are not necessarily business related. They're more society related, climate related, market related, not necessarily business decisions. So those indexes usually don't change that much. Okay. So the first half of the year, and to make sure that you have enough resources to satisfy it. So here is if you're budgeted dollars here, you don't want your budget to be, let's say, $100,000 every quarter. No. The first half of the year, you want 290, not 200, almost 50% more. Well, what about the last two? Well, you don't want 200, you only need 110. Okay? But now you guys can probably think of a scenario at the beginning of the year, the people who do the budgets, who are not operations people, you get $400,000 next year as your budget. I'm budgeting you 100, 100, 100, 100 every quarter. And you raise your hand and say, wait a minute, no. The first half of the year, I'm going to need 290 budgets, 290K to budget. It says, no, half of 400 is 200, that's all you're getting. I'm going to need, why do you need 200? Only half, because I have indexes. Well, your index is 200, use it. We do the budget, you do the operations. Well, halfway through the year, if you're budgeted 200 and spend 290, then the last half of the year, they're probably going to increase your budget. I don't want to increase it. I want to decrease it from 200 down to 110. And they say, no, the first half of the year, your budget 200, you spend 290. Obviously, you're increasing your spending because operations don't know how to manage things. And so we're just going to give you even more the last half of the year, and you spend 110. All of a sudden, you get this vicious cycle. And this is what happens when a business is run merely by silos. People don't communicate within one another, and you don't respect one another. Respect each other's comments, perspectives, and try to come together. Okay, let's go on. Next year's, okay, let's move away from the example of a stationary time series. Let's go to a non-stationary time series. Next year's seasonally adjusted quarterly forecast is a trend according to this regression equation. I'm trying to simplify this. Craig, you're right. I'm trying to simplify this. So next year, I have my intercept of 50, my slope of 10, and so next year, quarter 1, 2, 3, 4. So my seasonally adjusted is going to be 60, 70, 80, 90. So we know next year, my seasonally adjusted is 60, 70, 80, 90, but I know there's seasonality. So I know what my trend is going to be, but I don't know what my forecasts are. Well, how can I put forecast in seasonality into those seasonally adjusted? You multiply by your indexes, and that's what I'm doing over here. If you multiply, there's my seasonal forecast: 7, 8, 1, 12, 72, and 18. Okay. Now, in class, I give examples and et cetera, and I'm pretty sure I do this also in the videos. I give examples of this. I don't do it in my lecture because everything is together, but notice my videos are spread out. You can focus on a presentation in my website, mdharper.com, with the different videos. Okay, the last one is even more powerful. On these two, I have a seasonally adjusted to transform to a seasonal value. Here, I'm going the other way. I'm taking a seasonal value to determine my seasonally adjusted. So for the seasonally quarterly time series of this, what's my seasonally adjusted time series? If I want to take seasonality out, I divide by my indexes. And that's what I'm doing here. Now, although I'm not going to illustrate it here graphically, let me appeal to your visualize these numbers on a graph. Okay, I didn't come prepared to do a graph. I do the graph in class. I also do the graph in some of my videos. Okay, next, let's say that we have 65, 96, 72, 24. And so they say, okay, this was our actual demand. Say this is in thousands or millions or something. And so they say, yeah. And then there's announcements that, well, next year there's going to be a trend. We have a trend. And so have I mentioned Roger in here yet? Anyway, so someone looked at this and says, oh, I see the trend 96, 72, 24, 96, 72, 24. I see the trend. The trend is negative. I know regression. I think I've mentioned Roger. Roger always comes up and he thinks he knows everything, and he does know some things, but he always says things wrong because he's too confident. Okay? I know regression. I can apply regression to 96, 72, and 24 and regress. So next year, our forecast is going to be negative. No, Roger, that's wrong. It's not negative. They go, no, it's not wrong. Who do you got working for you anyway? Anyway, I said, no, Roger, just sit there and watch. They go, no, it's positive. Do you have Rogers working in your company? Anyway, no, it's positive because we're growing, we're building. But it looks negative, 96, 72, 24. It goes up, but it comes back down. It looks negative. It's a negative trend. What do you mean positive? It's not positive. I can see it. No, because there's a seasonal component, and that seasonal component is so large. The magnitude is so powerful, it's hiding the trend component. Now, if the seasonal component here is hiding the trend component, then how do you see the trend component? You filter out the seasonal component, and the trend component emerges. How do you filter it out? You divide by the indexes. So I divide by my indexes, and the actual seasonally adjusted time series next year is 50, 60, 80, 120, 50, 60. There's my positive trend. You would never see that positive trend by just looking at the data. Seasonally adjusting it, taking away the seasonal component, and the trend will emerge. And that's called decomposing the time series. And that's how you do it. It's not hard, but it's not obvious. If you know how to do it, it's really simple. And I'll give you some templates on my website and also templates in Canvas to actually work these things. You just plug and crank. But you know what you're doing. You know what you're doing. It's not hard, but it's not obvious. But once you see how to do it, you can do these things. And these are really common 3 applications using indexes. Now then, let's put it all together. Putting it all together. This is called decomposition of time series. Okay, here we go. I have a time series over here, a quarterly time series. And this quarterly time series down here is 20 quarters. And so I plot it. Always plot your data. So I plot it. And series is my this triangle here. The diamond, I mean. It's not a triangle, it's a diamond. It goes, there it is, ding-ding, ding-ding. Well, first of all, I can tell there's a trend. I have a trend, I can see it there, it's going up. I have a trend component. And the second is that, well, it's a quarterly time series. So let's look at 4 quarters. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Well, I can tell every year there's a pattern. It goes up and comes down, goes up and down, up and down, up and down. So there's a pattern that repeats that's a seasonal component because the pattern repeats every year. I have a trend component, I have a seasonal component. Okay, so if you have a seasonal component, then the first thing you do is block the data. So I'm blocking it. It's quarterly time series. So the first year is my first 4 quarters. The second year, next 4 quarters, 4 quarters. I have 5 years worth of quarterly data. And there it is. Now, I also know there's a trend component. So I know the difference between quarter 1 of year 1 and quarter 1 of year 2 is not constant. It's not stationary. It's non-stationary. The difference is a trend. This is a trend, 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 trend. So there's a trend here. So I want the slope of my regression line because the slope of my linear regression line is my trend component. So I take the slope, and I'm using Excel. This is my y variables, 1, 2, 3, 4, 5 is my x variables, and this is going to be my slope. So that's the actual slope or the trend. A slope is the estimate of the trend line, the trend component. I do the same thing for quarter 2, quarter 3, and quarter 4. When I look at the trend here, the slope, they're not the same. Why? Because when I see the first quarter increasing, the second quarter increases much greater. Why? Because of seasonality. Because in the first quarter, I have the seasonal contribution at the beginning of the year. The second quarter, I have another seasonal contribution, which is different. So the seasonal contribution is different throughout the year because I have a seasonal component. Okay? But since seasonality is in the slope or the trend, I can average that, and that's my seasonally adjusted trend. These are my seasonal trends. That's my seasonally adjusted trend. We'll see that in a minute. I can divide through by the seasonally adjusted, and I get my indexes. I would be curious to know year 5, quarter 4. Year 5, quarter 4, 120. Who knows? That's what we observe. Well, first of all, mathematically, we have a trend and we have seasonality. That's one thing. So we have a trend and seasonality right here. These two things right here together to estimate a forecast. But what actually causing that value, that's what we observe. Don't know. Okay. Forget that. Okay. Those are the questions that should be asked, you know. Says, oh, never mind. You don't learn without asking questions. That's I like that. Okay. So there's our forecast. Wait a minute. How to get these forecasts? Well, a lot of ways. First of all, I know that it's a trend here. So I can take my intercept and slope from this quarter 1 and put year 6 in there and get my forecast. Or I can take the slope, 48 plus 252, and get 300. I could do that too. And I only do that because my error is very, very small. Actually, it's 0 because I'm illustrating the techniques here. But do I need my indexes? Not really. I don't need them here. But how can I use them? Well, I can take my indexes and divide my time series by my indexes to seasonally adjust my time series. Why would I do that? Let me show you. So I take 60 and divide by 1.2, I get 50. I get 96 divided by 1.6, I get 60. So I take my time series and divide by the indexes, which are associated to the quarter that's in. So I divide these 5 numbers, each one of these by 1.2, and I get these seasonally adjusted values in the first quarter of the first 5 years. I take these, divide by the index to seasonally adjusted values. I take these divided by 0.7, these divided by 0.5. And there they are. So then I plot my seasonally adjusted time series. I plot this time series. And I did, and that's my squares here. And notice my trend line. It's a nice continuous trend underlying. When I seasonally adjust my time series, what emerges is the continuous trend. So what I just did here to get this continuous trend, that's exactly, let's back up here, that's exactly this third application. So that's exactly what I did here at the bottom. And then I plotted it. There it is. Bing, 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 ding, 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 ding. Okay. And then my forecast down there, this right here, I put it right here and highlighted it. Now, a little bit more on some terminology. Notice that this is a quarterly time series because every quarter I have aggregated data, going back to the original definitions. It's a quarterly time series. But then the annual trend of the quarterly time series, the annual trend is 50 to 90, is going to be 40. 59 is 40. 91 third is 40. So the annual trend of the seasonally adjusted time series of a quarterly time series is 40. The quarterly trend of a seasonally adjusted quarterly time series is 10. So annual is 40, quarterly is 10, trend. Now I could add up these numbers. I didn't do it. I probably should have, to get the annual time series. If you add this, the sum here, sum here, sum, this would be the annual. What would be the annual trend of an annual time series? Well, it's going to be 10, 20, 30, 40. This is going to be 40, right? So 40 times 4 is 160. So you can see that. But so there's some definitions from this. Okay. Now, and I go over this again in more detail in the videos. But this is example 1. Let me go to example number 2. Example 2 here, putting it all together. Now, example 2, the procedure is identical. I go through the very same thing. I take this, I plot it, I see there's a trend in a seasonal component, I block it, I get the slope, I get the indexes, I get the forecast, seasonally adjusted time series, I plot it. I do everything identical. The mechanics are identical. I don't do anything different. The numbers are different, but the mechanics are identical. But look what happens when I get done. Here's my forecast, but look at my trend. My trend is a step function. So when I look, if I took out the step function here, when I look at this time series, and I look at this time series, I'll say, there's no difference. It's the same trend. It's not the same trend. This is a continuous trend, and this is a step function trend. And a continuous trend, quite often, the continuous trend is like in retail sales. A step function quite often is with contracted companies, like design, build, construction companies, or the contracted with the government, like Boeing or Lockheed Martin. You'll have contracts, government contracts. So it's going to be, and then you have more contracts, or renew the contracts. So you'll have step functions in there. Well, to know what's going to be coming in the next quarter or the next year, this kind of trend here is used, decompose a time series to know what kind of trend you have, to know how to put it back together to get a very accurate forecast. And people who do this over and over and over again, decompose, and focus on the components, focus on the seasonality, focus on the different trends, and put them back together, get very good forecasts, very accurate forecasts. The more accurate your forecasts are, the better your operations, and the lower your cost, and you're right on target with your estimates. And so forecasting can be extremely powerful. Now, down here I did the very same thing, but I did it with filtering instead of blocking. We won't do this in this course, but I put it in here because sometimes people do ask about it. And in the future, if people are interested and they try it and they want to know more about it, and here's the steps that I went through when I did this. And I can talk about it when it's used, when it's not used. In this course, we'll use blocking. Filtering can be used, but only in certain circumstances, and we can talk about those if you're interested, but not today. The last thing I'm going to cover is exponential smoothing as an introduction to forecasting. And then next week, in my lecture, I'll probably go a little bit deeper into this stuff. Probably focus on nonlinear trends. Okay, exponential smoothing. The idea here is a forecast for tomorrow is a combination of the data we observed today and the last forecast that we had for today. So we have our data and our forecast. We compare the two. And we use a comparison of these two numbers to forecast the future. Okay, and we put them together with alpha, which is a smoothing constant, which ranges between 0 and 1. And so the idea here, since alpha ranges between 0 and 1, then the idea is that here's my data and here's my forecast. If the forecast is up here, then I probably will adjust this forecast. Since I observed something below my forecast, I'll probably adjust my forecast down a little bit. But if I observe something above my last forecast, I'll probably adjust this up a little bit. And how much I adjust it is dependent on alpha. So if alpha is 1, then here's my last forecast. Here's my observed data, if alpha is 1, my forecast is just going to be the data. I'm going to ignore the last forecast. But if alpha is 0, then here's my forecast, here's my data. I ignore my data, my forecast just stays at my forecast. But usually in exponential smoothing, it's somewhere between the two. So that's kind of what's happening. But this kind of forecast, exponential smoothing, is very appealing to business because this is how humans naturally make forecasts or make predictions. For example, they have experience. I've seen it before. I think this is going to happen. Then all of a sudden they observe something that deviates from what they expect. And that experience will adjust your forecast for the future. So there's a natural human element to this. And people feel very comfortable about that. Let's adjust it because we have observed something a little bit different. Okay, now alpha, we'll talk about how alpha in a minute. How to find alpha. We'll talk about Omar's 75. We'll talk about where alpha comes from in a minute and how to adjust it. Here's where we come into the adaptive forecasting in just a second. So let's do the arithmetic. Okay, so let's take this down here in the equation. Let's let alpha be 0.2, set it at 0.2. If alpha is 0.2, 1 minus alpha is 0.8, so I have 0.2 here for alpha, 0.8 here for 1 minus alpha. So this demand here is given. So we have a demand that's given. And so now we have an alpha, we have a demand, we have 1 minus alpha, but we do not have an F. So we need to have a forecast to start this. We don't have a forecast to begin with. So there's all different ways of generating the first forecast. For this course, to keep it simple and easy, I'll take the demand data in the first time period and I'll copy it down as the forecast for the second time period. That 200 is 200. So now the second time period, I have a 210 and I have a 200. Now I can do the method. So I bring the 210 over for my D, 200 over for my F. I'll multiply, I'll add, and that 202 then becomes my forecast for the next time period. I bring those over, 225 over for my D, 202 over for my F. I multiply, I add, and that becomes my forecast for the next time period, 206.6. And I just keep, that's called an iteration. I just keep going down and keep going down until I hit the bottom, and there's my forecast. Now, so that's the mechanics. But exponential smoothing really is a moving average. Okay, it's a moving average. But it's not a fixed window. Now our fixed window is an equally weighted moving average because we weight each number equally when we take the average. We add them up and divide by the number in the sum. Leslie, Boeing example. Well, they will have contracts with government, with industry, with the military. They have different large corporations will have multiple contracts, and those contracts will have a tenure to them. And when those contracts are close to being over, they can renew contracts to make more or renew for other new products. And so once you have a contract, then that's going to be a constant demand until all of those items are being, you have a contract for 20 planes, that kind of thing. In my work, if material planners overshoot, we have suppliers requesting millions of obsolescent claims. If they understood, we're lined down at the factories. Yes, as a matter of fact, sometimes you overshoot to have secondary markets, and sometimes if you overshoot materials, sometimes you plan it that way. And as it turns out, in inventory control theory, we'll talk about this later, overshooting is much better than undershooting, because if you have extra inventory, the cost is not that great, but that extra inventory could have a secondary market, and that secondary market can create new projects and new contracts. And so that's the business side of it. That's more of a strategic side of it rather than just the operations side. It doesn't seem like exponential smoothing provides a very close forecast to actual demand. But there's some value to this, Dana. There's some value. Let me finish up and let me show you. There's some value to this. Let me go on, then I'll come back to the questions. So I'll be getting to answering those here, but once I get done. Exponential smoothing is a moving average, where a moving average is equally weighted. Exponential smoothing is a non-equally weighted moving average. It's a weighted moving average, where the weights are exponential weights. And I think in the videos, I illustrate that it's exponentially decreasing as it goes back. So a moving average has a fixed window. Exponential smoothing theoretically has an infinite window. It goes back to infinity because it just keeps going down, and the exponential weights get smaller and smaller and smaller. Theoretically, it goes to infinity, but it gets so small it's insignificant. So you do cut it off. So therefore, when we apply this, we don't have a window. We use all the data when we use exponential smoothing in this course, in the homework, and even the exams. But you'll see in the exams are very different than the homework. Okay, and this lends itself to Excel quite well, which we'll see probably next week. Now, the interpretation. Here comes the interpretation on alpha. Remember I mentioned if alpha gets to be large, then large alpha follows the data. But since exponential smoothing is the same as a window, moving average window, then following the data is the same as short window characteristics. Okay, short window characteristics will follow the data quite well. Will follow the data, which has an enhanced impulse response. So if you want to decrease, if you have a lot of impulses, then you want to decrease that window, increase alpha, which is equivalent to shortening the window to enhance your impulse response. Small alpha, on the other hand, lowers the influence of the data and just follows the last forecast, which is the last long window characteristic, enhanced noise dampening. So increasing and decreasing alpha has the effect of enhanced impulse response and enhanced noise dampening, going back and forth, back and forth. And remember, you're using all the data. And you're just increasing the most recent or decreasing the most recent. So you're just increasing and decreasing. This exponential smoothing is just migrating like this. Well, traditionally, alpha starts relatively small. Small because we want to have stable forecasts. So they'll start 0.1, 0.2. That's what companies usually do in practice. But if they see an impulse, they want to respond to it, they will increase alpha. By how much? It's a business decision, management decision. And sometimes it's tiered. Sometimes it's tied directly to the increase of your impulse. But how do you know you have a significant, how do you know when you have an impulse, how do you know that impulse is significant? Well, there's where the tracking signal comes in. The tracking signal will tell you if you have a significant bias or not. And that bias is because you have observed data and a forecast, which is an impulse which doesn't meet that. That bias then becomes significant when the tracking signal becomes significant in magnitude. And so what companies will do is tie the value of alpha somehow to the tracking signal. And if the tracking signal gets large, alpha will get large. Again, sometimes it's direct one-to-one mapping with a parameter, or sometimes it's tiered. So if it's in here, it's going to be this value. If it's between these values, if the tracking signal is here, then alpha will be increased to 0.5 or 0.6 or something like that until the tracking signal goes back down, and then alpha will go back down to 0.2 or 0.1 to stabilize your forecasts out. And so it's just the alpha and tracking signal are matched, and so that's essentially referred to as adaptive. You're adaptive forecasting. You're adapting your technique to whatever's happening in the data. Well, if you think about that, that's essentially the same as artificial intelligence. It's thinking about it, but you're telling it how to think. It's thinking on how you adjust your parameter, alpha, how to adjust that relative to whatever's happening, bias is happening in your time series, in your forecast, to reduce that to have better forecasts. And as it turns out, this can be automated. And so this can be used when you have hundreds and thousands of items in the manufacturing or service industry. You have a lot of items, like Amazon.com. They have hundreds of thousands of items. And how do they keep track of all that? They have to have some automated way to track inventory. And this is one way of doing it quite effectively. And I don't know if they do it exactly like this, but this is the kind of techniques that can be used in those situations. Okay, and that's what I mean by, and there's where alpha can be adjusted very practically. Now you can do it by hand, or you can do it automated, but however you do it, it's going to be extremely effective. As it turns out, it's much better than going into 100 to 200 or 100,000 or 50, 80,000 items and trying to do it by hand, or flagging it and wondering what to do. You automate it. And if you automate things, you can look at the quarterly statements and say, how we measure this dollar-wise, how we measure this shortage-wise. We can have different metrics in inventory, and we'll be talking about those metrics in inventory control theory. Okay? So now let's see if I've covered everything. It doesn't seem like provides very close forecast to actual demand. Exactly. I'm in global at Tesla. Oh, cool. Now, okay, exponential smoothing. Notice it is a exponential smoothing is like a, how can I say this? It's an iterative technique. Notice how this is an iterative technique. Iterative. So this is the period could be a week, could be a quarter, but at Tesla, or if you're doing very high-end type of you're not really adjusting your forecast on a weekly basis. That's what I'm getting at. The product you have is maybe your forecast maybe be on an annual basis, or your forecast you can actually look at your global supply chain. And we'll look at global supply chain management in my supply chain course. But when you look at global supply chains, a lot of times that demand has a lot of moving parts, not just one market, not just one type of supply chain design. And you can have your parts called delayed differentiation down. And so the exponential smoothing could be used upstream on your supply chain because you do have a lot of component parts. But as you move downstream, you move away from exponential smoothing to something a little bit more accurate by looking at more regression or multiple regression and causal regression for demand downstream. But as the demand comes upstream, you have your bullwhip effect, and you're going to have more exponential smoothing. That gets away from this course, but very good point, Wesley. Leslie. Very good point about the supply chain. It really depends on the product and depends on where you use this stuff. But understanding the mechanics and understanding the concepts and the techniques to understand when to use them, where to use them, and how to use them, and why to use them. Sometimes you do, sometimes you'll use them and then you'll shift, you'll change. But that's why you have operations people doing operations. You don't blindly apply these techniques. You understand what's happening and apply them strategically and agile. You can change and shift to something different very quickly because you know the properties and the characteristics. Well, today, so very good. Now notice further down here, I go deeper, and I'll do this next week. 2-parameter, 3-parameter exponential smoothing. And down there, I think I have nonlinear trends, and I have some Excel spreadsheets and templates. And so next week is when I do go deeper in this. Go deeper into this in looking at more sophisticated ways of doing it. Actually, this level is like an upper graduate, a lower introductory graduate level. The next week is going to be pretty much mid-level, graduate level. Things that, again, practical things that you will need when you start doing forecasting in business, depending on whatever company you work for. But it's important to get the fundamentals. That's what I did today. It's important to get the tools and the mechanics, and then understand the concepts, and then you can start applying them strategically and tactically and to achieve what you want to achieve. So that's where we're going in this course. And that's all I have for today. Hey, I want to tell you how much I appreciate these all the questions. And again, bringing Canvas back up. right here, this is in the, let's go back to home. Under home, down here on forecasting right here, weeks 2 and 3. Right here under videos. Under video forecasting, this is going to be a video. It's 2.5 hours. Yeah, almost 2.5 hours. Regular class period. It'll be right here. This will be a video probably tomorrow sometime. But and then next week I'll be talking about the quizzes and then the homeworks and then the assignments. And so each time these are due, I'll be talking about each one of these. Okay. Next week will be the next topic and then the quizzes. Okay. Good. Well, that's all I have for today. And I hope this helps. And I want to encourage you to use the resources, especially the videos. Then I have my notes on Canvas. And some people like reading the textbook. They don't have the exact focus I have. Sometimes they cover things I don't cover. Sometimes I cover things they don't cover. But I cover things from my experience that I think are valuable and are useful and are practical out there. And so use the resources. And so work this week. I have office hours Monday, Wednesday, and Friday at 7 p.m. The click is in Canvas again. Come and ask questions, and we're getting started. This is the launch. Now we're getting deep into this material. We're getting deeper and deeper and deeper as we go. And when we get deeper, it gets better and better, and it gets really fun, really exciting, very practical stuff. Sometimes it's easy, but it's not obvious. Okay, that's all I have for today. Thank you very much for all of your questions. I really do appreciate them. So between now and the next time I see you,